Today we're going to talk about some general misconceptions about the use of microwaves. I've got two identical Panasonic microwaves here, brand new. What I'm going to do is to take one of these apart so we can show the internal components of it. And then the second one is what we're going to experiment to dispel some of those misconceptions. Inside of this, as you can see, there is a waveguide which is covered by a plate. This is what you see inside every home microwave. We're going to take the top cover off. On the side here, we have some general major components which we have already gotten loose. The first and most important thing is the magnetron, shown here with the antenna where the microwave's coming out. Behind the magnetron, we have a little waveguide, just a small piece where the waves are sent in to go inside the microwave to cook. Here's the door switch. The length of the waveguide is just about 3 centimeters. The first misconception is that the waveguide has to be short and the cooking chamber has to be cubical. But waveguides are designed to carry electromagnetic radio waves, and they don't have to be short. They can come in a variety of lengths and shapes. They can be bolted together to increase their lengths. They can go around the corner. They could be welded in different shapes. In fact, they can even come in flexible forms. The second misconception is that you cannot put metals in microwaves. The reason that some metals arc or spark in microwave will be discussed in another video. But in general, we can put non-magnetic metals like copper, aluminum, and stainless steel in microwaves. There's no sign of any arcing. Now that we know microwaves can travel through waveguides, and also microwaves can be applied to non-magnetic metals, let's see if we can combine the two concepts and see if we can cook differently. First, we adapt a metal plate to cover the waveguide inside the microwave. So the plan is to attach this plate with the waveguide to cover the waveguide of the microwave. Place the plate in the microwave and mark where we need to cut the holes. So now we're going to extend the waveguide and bring it out of the microwave like this. We've got an elbow and tie into another waveguide. And now once we bolt these together, the waveguide will be completely out of the microwave chamber. We put a few bolts to temporarily keep it in place while we reach out to the back side. It was somewhat of a challenge to tighten all the bolts, but with a little bit of creativity, everything got together. Since microwave can be applied to non-magnetic metals, how about if we try to connect our microwave waveguide to a stainless steel cooking pot? This is a 10-gallon stainless steel cooking pot, typical of larger pots used in kitchens. And the challenge is to either attach the waveguide to the top or to the side of the pot. Our company, WaveTech, has a patent on a special window with a sapphire barrier that allows all the microwaves to come in and none to reflect. And so we have basically modified this pot to attach a waveguide to it with our glass barrier inside. This is a rather crude arrangement. We basically cut a hole in the pot and attach a waveguide using one of our sapphire barriers. So the idea is to line up the waveguide on our cooking pot to the waveguide that is coming out of the microwave. With all the bolts on, now this system is ready for trial. All we have to do is put some water in the pot, bypass the safety switch on the door, and turn the microwave on. We'll be using a microwave leak detector or survey meter to make sure that once we turn the microwave on, if there are any leakage, we can quickly take care of that. There is a gauge on the pot that shows the temperature, but just to be sure, we're going to check the water temperature, 59 degrees Fahrenheit. The best thing is to basically steal the locking mechanism from the other microwave and bring it over to try to cheat the door switch. By adding some weight to this mechanism here, we can ensure the light stays off. That means the door is closed. And then while it's running, we'll use the microwave leak detector, see if we feel any leaks or find any leaks. Now we're going to do 20 seconds and then check for leaks. No microwave leaks anywhere. Seems like everything is working okay. Now we're going to set this up for 20 minutes and monitor the temperature. This is the start of the 20 minutes. Temperature is going up degrees Fahrenheit, about 90 degrees. The end of our time. Temperature just about 104 degrees Fahrenheit. I hope this video generates some new ideas about a safer and more efficient way of cooking in the future. We have used this concept for over 15 years and have produced millions of pounds of products. The concept can be easily adapted to much larger industrial food processing vessels that work with microwaves from 75 to 100 kilowatt of power.